basis of geographical information systems. Now, these are, as I'm going to talk about in the lecture, they are based on the advances that have happened in computing over the last few years. GIS becomes possible because of the vast increase in computer processing time. It's so much quicker, more storage, because they, as you'll see in a moment, they can involve vast amounts of data, and you're doing calculations based on spatial information. So there's a vast number of programs that you can buy, some of them extremely expensive. And one of the best ones is ArcGIS, which we won't be going into because, in my view, in order to access data and be able to get to do GIS, at least in the first instance, the best way to do it is to use what's called Google Earth Engine, which is what I'm going to introduce you to today. And you'll see that in the notes, we've got this lecture demo PDF, which is what I'm going to go through. And later in the lecture, after the first part, I'm going to go and take you into, this is Google Earth Engine, and we'll go through and we'll be looking at how that works. Now, what that opens up, because what Google Earth Engine can access is every single satellite photo taken by a non-military satellite for the last 50 years. It's an amazing resource, and it keeps compiling it. Every day, satellites go over the Earth compiling pictures, and they get put into the database. So the thing is constantly expanding, and you can access it for free. And you will find that many of the things labeled Internet of Things and sold as commercial products to help people do environmental monitoring and assessment using satellite data are actually running through this. So what the company has done, they've tailored the Google Earth Engine to provide a solution. I'll just give you one example, though. This is not, you don't have to pay for this one. This is done by CSIRO, and this is typical of what an output from Google Earth Engine might look like, and it's for working out irrigation needs. So this is used in agriculture, and you can work out on a field basis based on different satellites what are your irrigation needs for a particular field, and it will work out the evapotranspiration of your plants, how much water they're losing, how much water do you need to add. So it's just one example of an Internet of Things solution using what is free software. And that's what I think you should be thinking about, is that you can develop your own software for your own problems in environmental science, and using what is essentially a free resource. And I'm going to show you how to start doing that. But in order to do that, I'll just close that one. I'm going to first just run through what is remote sensing in environmental science. So I'm going to give you what I hope not too long a background. I don't want to go into detail because you can do it, much of it you can do without going too much into the detail of the theory of it. So I'm going to give you a quick introduction to environmental remote sensing using satellite imaging. Okay, so every day, as you undoubtedly know, there are satellites circumnavigating. Well, they're usually circumnavigating the Earth on different pathways, and what they're doing is exactly what this image shows. They're collecting boxes, actually boxes rather than lines of data, so that it will take a time-lapse box photo and produce a mosaic around a stripe in the Earth, and then the next stripe. It may not completely overlap with the previous one, but eventually over a couple of orbits of the Earth, you will get a map of the entire Earth's surface at a certain resolution. And this is, there are so many of these satellites up there now. producing different types of data, working for different companies. As I said, one of the beauties is that European Space Agency and the NASA have both made their satellite imagery, their public satellite imagery, open to the public. You can access it using Google. Google collects it, stores it on some vast computer somewhere, and then you can access it. So remote sensing as a science comes from aerial photography. As soon as people could get off the Earth's surface with a camera, off they went doing aerial photography. And of course, that's driven largely by military and geological surveys. So they wanted to see from above. They use the basics of electromagnetic radiation. That's visible spectrum at that time. And then they look at the spectral properties of vegetation, soil, and water. Each of them, as we'll see in a moment, each type of thing that the light impacts, be it vegetation, soil, or water, reacts differently with the incoming light, and it might absorb some wavebands of light, or it might emit them, or it might fluoresce. So whatever we're doing, whatever we're looking at has a characteristic that we can then register it as characteristic of that kind of thing, of either soil, water, or vegetation. What happens then is if you get a characteristic of a particular type of structure on the Earth's surface, say this purple as kind of rocks or something, then you can classify it. What you can do is you tell the computer, go find everything that's purple, and it will search and do a more or less good capture of everything that has been registered with those spatial characteristics that you've given it. And that allows us to do remote sensing of vegetation, and we can work out vegetation indices, which I'll talk to you in a moment about, which we'll actually do in the class a bit later. So obviously, because there was some of these wacky things from the early 1900s, the early remote sensing of Australia was part of the geosciences, because the main driver in this country was, apart from expansion of agriculture, the availability of water, was finding mineral resources. So there was a big push here, big early push in this country, as early as they could get planes in the air. And then this, as I said, the other driver for this is warfare, that they were taking pictures of trenches during the First World War. Now, very quickly, they realized that they could get better detail and better view if they actually took two shots. So a stereo pair of pictures taken by the same camera, slightly off-lined, produces what comes to a 3D image. Okay, so they're adding a third dimension to it by taking two images, but at slightly different, simultaneously, but at slightly different positions. And that gave depth to the photo, some degree of depth. Again, it was driven by the military and the First World War. That's when they started using it, and they had this stereo viewer for viewing these images. And what happens is that if you take a picture from two different positions, you get a slightly different perspective on it. And it's just like your eyes work. You know, we have two eyes, and because we have two eyes, we can judge depth and reach out with a hand and pick something up, or we realize how far something is away. Otherwise, the image appears flat. So by using stereoscopy, we can give depth to our image, and that's why we have eyes on the front of our head, which are slightly two different positions, and our brain functions to separate those images out. Now, here's the kind of vegetation maps that you produce. And what's happened is that whoever's produced these would be oldish, but so they've been done by hand. They've determined that all of the vegetation of a certain type fits in that field. sits in this area, and then they classify it. So this is classified. They then produce their classifications based on the characteristics that they've obtained from the aerial images. Now, what we do in GIS these days is we do that as a semi-automated process. We will see if we get that far through the tutorial, through the classes, that it's actually quite difficult to do, to get it right. The computer does get confused by the different images, but we can certainly improve on this kind of gross classification, which is what was available using aerial imaging and just people looking at the aerial images to determine what they were seeing. If you look on this side, this is a more detailed geological map. So today's aerial photography takes place, you'll all be familiar with Google Earth or Nearmap, and they produce visual images of the Earth's surface. So we can get aerial images from satellites, which are at least as detailed as the old ones that used to be produced here by aerial photography. And that's just an advance that's happened in the last few years because of the, well, driven by things like smartphones. The resolution of lenses has become amazing. And then what happens afterwards when you capture that image is that it then resolves it into using computer software into a very, very high detail, high resolution image. And of course, then what we could do is do exactly what we said before, is we could recognize this as a certain type of vegetation. So click it, we teach the computer the basis of what's called artificial intelligence, is that you teach it, this is, we'll call this, say, mountains. And we teach the computer, tick, 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 these are the characteristics of what a mountain looks like. And then we tell it to search the engine for every other instance of what we've called mountains. Now, if we did that with the what is mountains here, we are likely to pick up things which may or may not be, I don't know the area, but these may or may not be mountains, but it would pick up everything that looks similar in color to that. And then we could tell it to look for agricultural fields. And we'd click on this and it would pick up the fields like that. And this is actually, as you may have recognized, this is of our campus. So here's the Richmond Air Base. Here's the race course. Here's the campus itself with the golf course next to the station. And this is our land. And so this is bushland around the outside coming up as one color, and then the farmland coming up as the other. And we could pick up using different indices. We could pick up the difference between arable farmland and say this high intensity horticulture that's going along the river banks. Now, of course, the next game changer, which is we're still in the process of dealing with, is that we don't have to rely nowadays on satellites. We can move to unmanned aerial vehicles or drones, and we can put the same kind of high resolution cameras onto a drone, which has now become more and more stable. The platforms. Is the airbase? Yes, it is, but it doesn't mean stop us getting a picture of it. That airbase there, because that's Richmond Air Base. Yeah, that's in the satellite image. They don't blank them out. Okay. So now we can get this with a UAV. We can put the same kind of imaging satellites, software or hardware, sorry, cameras onto a drone, as we have basically in the satellites that are flying around the Earth. Now, the advantage of doing that, of course, is that we're moving closer to the Earth and we can make a much more localized mosaic. And in doing that, we can get much higher resolution than we can from a satellite image. Typically, a satellite image such as this is got, think about 10 meter resolution is the best that you can get at the moment from a non-military satellite. I wouldn't know what's available from a military satellite, but 10 millimeters is the size of it. So 10 meters is the size of a pixel on one of these images. To be frank, there's not much from a satellite image point of view, and for what we're doing with them, 10 meters is fine. You get most of your data, because if you go smaller, you'll just get more and more variation across the fields. And it'd be very difficult to classify it, because it won't recognize, it'll recognize every single pixel is different from every other pixel. Classification actually can get harder the more detail you have on the map. But we can now do it localized using drones, of course. There are issues over permission, and one of the best places actually to put drones up in Australia is over our campus because of the airbase. Instead of having to contact CASA in order to put a drone up, we just need to contact the airbase and ask you, are they dropping any parachutists today? And if they're not, then they'll give us permission to do it, which is why, if you look at the fields around this area on the river flats, it's why all of the remote controlled aeroplane clubs are all down there flying their planes, because it's so easy to get permission to put them up in the air. Okay, so 40 years is the, I think it's actually longer than that. Oh no, 40 years. Yeah, no, there was Landsat 7. So I think it's 50 years of Landsat. Landsat was the first satellite imagery put up by NASA. It's quite a large satellite at the time, and then it switched to Landsat 8 in 2013. So there was quite a few generations before that. It was put up specifically, it was the first satellite put up to get as commercial satellite to gather information on land areas. Okay, so there were military satellites before that. There are obviously other satellites that the government of America was using. This was the one that was first one that was made commercially available to everybody, and you could buy the satellite images from NASA. So this is where it all starts from. From then onwards, every agency is putting up satellites, and more of them are made available for free, as we'll see in a moment. So there's no need to pay for satellite imagery. I remember when I got my first satellite imagery of Vietnam for a project I was doing, it was so difficult to handle, because you buy the disc, you had to buy it was significantly expensive to buy an image. Then you had to put it into a specific software to process it. And if you were doing Landsat and what was called spot images, they were the two that were available. To align them and get them to sit on top of each other perfectly you had to do manually. And then you ended up with a massive file, which the computers at the time struggled to cope with in terms of processing it. So we've changed so much, as we'll see. Everything's changed in the last 10 years. The radiation that's collected by these things is across the whole range, up to the infrared and the microwave. There is no point in satellites collecting radio waves. The radio waves are collected by satellites, but they're usually pointing in the opposite direction, collecting radio waves and microwaves from space. We're really interested in the areas of infrared, the visible light, and not so much these things. The idea of a satellite zapping the Earth with gamma rays or X-rays is probably going to cause safety issues. So we do monitor UV. They do look for some X-rays, because they look for radioactivity on the Earth's surface. So they don't actually fire the light down. They measure the radiation across these 5 ranges. And you can see the only difference between an X-ray and a microwave, so the thing that can see inside you versus the light that cooks your dinner, is the length of the wavelength of the light. Okay, the short wavelengths are high energy, and then the long wavelengths are low energy. The long wavelengths tend to penetrate better. So it's a general rule that the the longer the wavelength is, the more it will penetrate something. So for instance, if I was going to look in, I wanted to look under the Earth's surface I'm on the surface of the Earth and I wanted to look down into the ground, then I'd be using microwaves, radio waves, and radar. That's it, these radio waves, and fire them into the ground, because these kind of light, these wavelengths, the high energy ones, don't penetrate. So light doesn't go into the soil, but radio waves do. So we'd use radar. The various bits of the spectrum which we classify, you see the visible light is just a tiny part of this enormous spectrum. Things like infrared light are split into short, medium, and long, well, near, medium, and far infrared. Okay. What do we do? Well, the light from the sun hits the surface. Some of that light is absorbed and disappears, or some of it penetrates the Earth. Some of it then is reflected, and it can be reflected, changed in two ways. It can change color. So it could be, you can see a color shift. So for instance, everything that is green appears green on Earth, like the trees. What they do is they absorb all of the red light, or a great proportion of the red light. So the red light part, the red part of the spectrum that hits the Earth gets absorbed by the trees, and then what gets sent back is green light. And so that goes back to the detector, which we've now put up in the satellite. You can also get some things delay the signal going back. And so what can happen is you can get what's called a phase shift. So there are two aspects to the light coming back. One is that it's altered in terms of its wavelength. Some wavelengths have disappeared, but also if it's slowed down by the interaction with the soil, what will happen is that it will be out of phase with what went in. So what was a peak in the wave now becomes a trough or whatever. It might cancel itself out. So you get phase shifts. Anyway, it gets back to the satellites. The light is reflected back to the satellite. It's then sent down to Earth. It is sent to a second satellite, which gives you, sent to the second satellite, which gives you a triangulated position for that thing. And then it's processed, both bits of information, both the position and the data are then processed and turned into a map. And you can see just on this map, one of the things is that they change the colors into three colors, RGB, red, green, blue. And every color, as you may well know, every color that we can see is a combination of red, green, and blue. But in the computer, they are actually split into red, green, and blue. And then where red and green overlap, you get the combination of red and green, whatever. So there's three layers. The bane of this is cloud, okay? And one of the things that we end up having to do when you're looking at satellite imagery is make sure we don't get atmospheric interference. Obviously red, as I said, red, some forms of infrared, sorry, some forms of infrared can get through the cloud. And what they do with that is just to recognize the amount of cloud cover. For everything else, like green, red, green, blue light, we get a problem. Well, you know that clouds scatter light. That's why they appear white in the sky. They scatter all the light that hits them, so we can't see through them. So we get scattering from the light. We get scattering. Not all of the light that hits the surface will be scattered straight off and be to the sensor and be detected. It will be scattered at all angles. The light that goes back also may get absorbed by the atmosphere, but these are all things that produce data, which is important. The absorption, the amount of absorption or the amount of loss of light can be really important in working out things like greenhouse gas effects or the greenhouse effects. If we're wanting to measure carbon dioxide in the atmosphere, we want to know is how much light due to carbon dioxide in a particular wavelength here, is failing to get back to the sensor. And that indeed is what we do to measure the amount of the buildup of CO2 in the atmosphere. So we can produce a map that shows that. And we can show that different parts of, we can show the pollutants. If we have a map of, and we're measuring CO2, the areas where high CO2 is occurring, emission is occurring, will show up on our map, and we could spot polluters using CO2 mapping if we wanted. So there's an infinite number of ways that you could ask questions of satellite imagery on a scale that's unprecedented. We're at a great moment with the free availability of the satellite imagery to ask all sorts of questions which we've been dying to ask, but unable to do so. So here's just a bit more complicated thing on what's happening. Don't need to worry about that. It's exactly the same diagram. Now, the spectral properties of surfaces do change. Most of the light is in the red, green, blue, and we can see that bare, dry soil will reflect the wavelengths mostly in the green and blue. Red will be absorbed because vegetation tends to absorb that. So here's we've got the absorbance from the vegetation. And the other thing is with clear bodies of water will often appear black in a satellite image unless they are severely polluted, in which case they can get a greeny tinge or a yellowy tinge, but they'll appear black because of the absorbance of it. The spectral properties now that we can get are very detailed, but of course we're not going to be using satellite imaging to do this. This is for remote, for other types of drones, land-based drones, where we can go and sample in very arid environments without sending humans off to do it. And we measure, here is the spectrum across the visible spectrum. Visible spectrum goes from about 400 to about 700, so it's about here, and into the infrared. And you can see that the information about the moisture content of that soil, which is what we're doing, the crust dry, crust wet, no crust wet. This is the absorbance of water in the infrared spectrum. There are two characteristic peaks from water, which you may remember from chemistry. That's here. Okay, that peak, that's the OH stretching. And then they have the bending moment of the water, which appears here. So in this region here, these regions of the infrared spectrum, you can measure quantitatively how much water is present in the soil. And so you can send it off to go and do that. You also get peaks in what's called the near infrared, in the far infrared, but the instruments to do that are not so useful. Those are maybe things that we get off the satellite. Actually, I haven't done that. I've never used those spectrum. But that definitely is common. It's an infrared spectrophotometer attached to a vehicle, which gives you a moisture content. So if we're searching for water, and obviously when they take things to Mars or put things on the moon, they're searching for water. This is how they do it. Now, the characteristics, as I've mentioned, of plants and vegetation change with the seasons. Okay, so if you go from a live leaf to a dead leaf, you get this kind of thing. But in the live version, they will absorb, the green leaf will absorb radiation at around 600, which is red, and into the infrared. So it will appear red when the red light will disappear. So it'll appear green because the red light disappears. And that's because the red light is getting absorbed inside the mesophyll of the plant, which is where it's the workhorse light for photosynthesis. Now, if we then focus our Google Earth engine, which we'll do in a bit, looking for vegetation, we can actually put what's called a false color onto the map, and detect everything. And usually what happens is that everything that is disappearing, the light that's disappearing, turns up as red. So this is a typical map. Now, just remember that that's a false color. It's not really that the trees are red. It's an image color created by the absorbance of light to get vegetation indices. And you can do this with different, you can see slightly, if you look carefully, different colored trees, different types of tree have different color absorbances. So you can actually differentiate tree types on the specific wavelengths that they're measuring. The only problem with that is, of course, that we can't tune the satellite to measure just the specific wavelengths. What we do is we gather all of the light in a broad band, which it calls red or far red or whatever, but we process it in order to separate it out. Here's what I was saying. Different types of crops at different stages have particular characteristics. Okay, so they absorb differently. So if you were able to differentiate, and particularly with drones, because you can tune them much more finely than you can the satellite, you can measure the absorbances at specific wavelengths, and the differences between them will tell you, if you know what the crop is, you'll know what stage of vegetative growth it's at, or whether it's not. And you can get things like heavy metal stress and plant stress. So lots of things that are coming now out of, this is the thing that's happening at the moment with the processing of data becoming so much easier, and the availability of images becoming, well, free. You can now start to differentiate crops based on the absorbance of light at different wavelengths. The number of satellite out there is phenomenal. This isn't even all of them. So we've still got the original Landsat. We've still got, sorry, not the original. There was Landsat 6 before that, but they've still got Landsat 7 up here. What else have we got? SAC, quick. Envirisat, Sage. I can't even see the European ones, which we're going to be using on this map, on this list. This is an old slide. Spot 4 and 5, remember I did mention Spot was one of the images, the first images that I bought for looking at archaeology. And I bought a Landsat image. It used to be phenomenally expensive and difficult, so difficult to process. Okay, so a system, I'm not going to go into too much detail, but has all sorts of satellite. So the satellite has many sensors on it. So one of the ones, there's different, each with different wave bands that it's collecting. So one satellite can do lots of jobs. And there's one here for MODIS, which we will be looking at later, which is global temperatures. This is the primary temperature difference. And when we set you an exercise on bushfires, that's the MODIS satellite, the MODIS sensor that you're going to be using. Okay, lots of new areas. This is the European Space Agency, has got Sentinel, which is one of the satellites that we will be using in a moment or two. It's really good. There's Sentinel 1, 2, and now there's Sentinel 3, and it collects, I think, 8 or 9 bands of data. You can download the individual images from there, but I think it's much easier, at least to start with, to go through Google Earth Engine, if only to make sure that you are getting a clear image. Again, the ESA gives all its data for free. You can access all of it for nothing, but and it's got all sorts of maps, and they're brilliant to, but the problem with doing them is you get one image down, and it's that image contains all of the data, and it's enormous. So you have a long time to download it, and manipulating it, you're back to the old thing of like my satellite or Spot or Landsat images, that you're having to do them all on your PC. The beauty of what I'm going to show you in a minute when we get onto Google Earth Engine is that not only is it free, but it does all of the processing in the cloud. So the only thing that you actually have to save and keep for yourself is your code to say, go to this map, do this, do this, do this with it, which is about 50 lines of text, which takes up no size. You know, the file size that you're keeping on your computer is tiny. Your instructions are tiny. They're just text. Everything is done on the Google Engine platform. Well, as soon as you start downloading, and I've got a couple of images I have downloaded, particularly clear ones, then you're having to process on your own computer. So I would recommend you still use Google Earth Engine, if only to search for very clear images, because otherwise you're searching through their catalog. It can take you ages. They collect so many images. There are ways in Google Earth you can search the catalog and identify a particular image, find its name, and then if you want to download that particular image, you go to ESA and download that image based on the name that it's got. Yeah, there's two types of orbit that we do. Is either we have well, there's a heck of a lot of debris out there. That's the point I wanted to make in this slide. But the other thing is we have geostationary orbits, and we have orbits where the satellite goes in a continuous orbit, but the Earth, because it's spinning, it'll just register stripe after stripe, so it's geostationary. Okay, so you can either be sun synchronous, low Earth, whatever. I'm not going too much into that. So a sun synchronous orbit, which is the ones that stay in the same place relative to the sun, but the Earth turning provides a different image each time, comes back, and I think it's about 6 or 7 passes, and it's back to where it started. No, sorry, about 22 days, I think, is the time it takes to get round to doing the same one again. You can see that the different types of satellite are in different orbits, hopefully not crashing into each other. There's always more going up every week. There's more and more junk up there. Okay, and this is where I want to get to. It's looking at Google Earth Engine, and we'll be using that. Okay. There are a few things just quickly to go through. We've got spatial resolution. How much is the size of a pixel on the ground, so that what it's measuring is an area of the ground. Obviously, if you look at movies, you would believe that satellites are capable of looking at people smiling from the Earth, and you can even see their teeth, or you can see the number plate on their car from above, or whatever. The surveillance kind of movies. That's not possible as far as I know. That maybe the military have got there, but we are usually working in the range of 10 to 20 square meters is per pixel. If we go much lower, we lose the resolution. If we go much higher, we get very high resolution, but it takes ages to collect the images, and the file size becomes absolutely enormous. Mixed pixels have different kinds of radiation within them, and remember I said that they collect them as red, green, and blue, so you'll have 3 layers. It collects a red image, a green layer, blue image. Yeah, great. 1 meter spatial resolution is fantastic, but it's actually quite difficult to ask questions about different types of soil using a very high resolution image, because there is so much variation happening within what is one type of vegetation. So 10 meter resolution is usually fine. Obviously great if you could do that, but it actually creates other images in terms of classification, problems in terms of classification. The kind of areas that we look, the visible spectrum is split up into 3: red, green, and blue. Okay, red, green, blue. Then most satellites will have a near infrared sensor, which becomes important particularly for vegetation, because this is the absorbance of from vegetation, and it's at its highest in the near infrared. Then you've got intermediate infrared, and you've got the shortwave infrared. So you've got two more vegetation indices out here. So there are about 7 which measure indices based on vegetation. There are other sensors as well. As I said, there's one for detecting clouds and things. We'll see those in a sec. What is happening now is, of course, with the satellites, these are moved on to planes. You get the same kind of hyperspectral imaging. Now, hyperspectral imaging is even higher resolution. Remember, the problem of these is that they are wave bands. You could split each of these wave bands into multiple bands and try and get the information, the details. I'll show me on the slide a second ago. This kind of fine detail information. That's quite difficult to get from a satellite image, to differentiate between different crops, because the width of the bandwidth that they are measuring naturally is quite wide because they're getting diffused by the atmosphere. Closer down to the soil, closer to the atmosphere, you can start to use hyperspectral imaging, and there's more and more of that going on with really small cameras that are not that expensive to try and get these fine-tune these peaks, these characteristic peaks of particular crops. So each pixel contains a unique spectrum of a particular wavelength, and the bands that they break them down to, instead of having one band for red, you can see that yellow is, for instance, is broken down into at least 3. There are many bands breaking down the bands that the overall bands of the color spectrum. When we classify, as I said, what we do is we teach the thing to come up with a likelihood. We click on the map and we click areas that we think are characteristic of that particular kind of vegetation, and it will measure the red, green, blue, and or whatever we tell it to measure as a characteristic of that thing. And then the artificial intelligence catches it. Now, AI is something that you'll hear an awful lot about at the moment, but all it is pattern recognition. So you have a body of information that you tell it to look at, and then you say how close, what percentage or likelihood is it that this thing that I'm looking at classifies as that, and that's why it's got these percentages. And if it's above a certain threshold, it will recognize it as that thing. So we call that unsupervised classification, and here's the kind of thing that we've got. Now, we can refine that through supervising it by telling it, okay, well, this isn't right, this one's not right. We can let the thing go, or we can tell it. So that's the difference between supervised and unsupervised classification. And then we split the things up into bands, okay, and we produce our classification map. So this is called feature extraction, and it's done by telling it, look for a kind of spectral response, and if it's above a certain percentage likelihood, yes, it's that. Now, we do have a couple of vegetation indices, which I'm not going to go in. The most important, the one that's most important is what's called NDVI. And as we'll see, we'll get onto that in this thing. It's the ratio between red and near infrared. So it's near infrared minus red, which we've already shown. Near infrared vegetation absorbs mostly in the near infrared. So near infrared minus red divided by near infrared plus red. So you get a fraction. And there's also the enhanced vegetation index. Again, I'll get into those later. And really, that's where I want to stop for now. And then I'm going to get on to the next part of the thing. So if anybody got any questions while I switch over. So I'm going to stop this. If any questions, even you, Ricky, if you've got any questions about what I've done so far.
I have a quick question.
Yeah, sure.
Is this like used or could be used to prevent disasters or to prevent problems, or is it not quick enough?
No, it can be, but again, it's a kind of like all in artificial intelligence. It's you build up the information of what could happen because of particular scenarios, and then you take your remediation forward based on the information of the past. So it will gather the information. Okay, let's look at floods. Okay, what's the likelihood if we get this much rain? What's the flooding effect going to be? Then you can remediate based on what you see, what the effect has been. It can't predict the future of nothing, but what is happening, and it's happening particularly the weather data, it is that you get weather stations which can do that now. It gathers a database of information and then produces likely outcomes, mostly in terms of crop growth, but certainly in terms of flooding as well. What would happen if? Okay, and it can issue an advanced flood warning based on, okay, you're getting characteristic weather patterns which caused floods in the past, and it will flash up on your phone and tell you there's a flood warning. Okay, based on information it's gathered from its artificial intelligence, from this kind of data. So it gathers the spatial the consequences, and then it's up to you to provide to link that into what's the likely scenario, what could go wrong, and what information are you looking at. We're going to do an exercise later, I think in the lab next week, on bushfire and the 2019 bushfires, and how the temperature data could be used to predict it. It could predict where the fires were going and things. Well, so, when you say the images are very large, when you down them, how large are we talking? We're talking many, many megabytes, or gigabytes, I think. I think it's about a gigabyte, to be honest, Jonathan. They are big, and the problem is not even that you can't download that and keep it on your computer. It's that when you want to, say, do a calculation, what you want to do is, say, take one picture away from another. So that means you have to have two images, and you want to see the difference between them. So you're taking one picture away. Every operation you do involves another temporary file. So very quickly, from two images that you're manipulating, or even one with multiple wave bands, you're generating maybe 20, 30 temporary files that are all swimming around in your computer, and it comes to a grinding halt. Okay. Any more questions? Anything else? Please, if you've got any questions, just ask. Okay, so what I'm going to do is, I've on the website, I've put here lecture demo, and in here some instructions on getting hold of Google Earth Engine. I'm a huge fan of this. The fact that Google will host these files, which means that all of your calculations can happen in the cloud, for the reasons I've just explained, with the size of files and the expense. Actually, the other thing is that as soon as you're manipulating things on your computer, you're having to buy software which costs many thousands of dollars. For some reason, GIS software is phenomenally expensive. So you have to keep buying the versions of that. This is all done free. It's the same data as that you would purchase. Well, actually, no, nowadays you wouldn't purchase it. It just is available free, even from the space agencies. They've made everything available free. You don't need to download it. What you can do is all your manipulations is you just call it up. Now, what you will have to do is register for Google Earth Engine. And in the instructions here, it tells you how to register. And once you're registered, you can use it for non-commercial uses. You can use it forever. We'll go through, and what we're going to do, well, I don't need to show you anymore, so let's do this. So what I'm going to do is go to my tutorial, and as it says, we have to register. You do a recount registration, and once that does that, we are ready to go. When you access it, once it comes back and acknowledges your registration, then you get access to this. Now, to register, I would strongly recommend that you get a Gmail account. It is a hell of a lot easier. And then whenever you log into Google, it will automatically put your password. You put your password in, but you don't have to keep typing it in every time you use it. When I go to this now, it opens straight up. Okay, my account opens straight up like that. So that's much easier. So register with a Gmail account if you can. If you're willing to. It's much easier.
Richard, sorry, I think this is hidden from us. We don't have this in our views.
Really? I thought that was there. It's just on the
Oh,
left.
it is. Yeah, no, she's right. She's absolutely right. Sorry. Yeah, thank you for pointing that out. Look.
As well.
Yeah.
That one.
That one is
yeah, okay.
Yeah. Yep, absolutely right. Thank you. God. Well,
the folder's there, isn't it?
Yeah, the folder's there, but
yeah,
what was in it wasn't. Okay, so there it is. It's there now. Okay. And if you want to go into it and get it onto your screen, we'll follow it through. Okay. Thank you for pointing that out. It's always terrible when that happens. Okay. So let's go back in here. So what I'm going to do is I'm going to follow this through. I'd ask you to, if you can now, open it up. And then what I'm going to do, because I'm going to pull that over to the other screen so that I can see it at the same time as I can see my Google Earth engine. So here, so I've now registered I've registered quite some time ago. It will open on the United States. Not a problem. We can go anywhere in here. Now, there are three main areas in the map, which I'll show you in a second. But what we're going to do, all of the things that we do in Google Earth Engine, we do in here. Now, it does require writing some computer script in what's called JavaScript. Now, JavaScript is one of the most common languages. It's used for all web-based stuff, which is why they use JavaScript in here. But honestly, don't get scared. It's the level of which you use it is so easy. Anybody can do it. As long as you can write English, you can write in JavaScript. It's very simple. And we could learn JavaScript, but there's really no point. You just use the instructions as you want them. Now, if you look at the things, we've got these four main areas, really. So I've got the script area. I've got a thing called a console inspector, and we use that to understand what maps we've got up on the screen. So the inspector will tell us about, it hasn't got anything in there at the moment, but that's where we'll see. And we can actually give it tasks to do. We can program tasks in it. The main things that you will see will be in here, obviously on this map. You can adjust the sizes of everything. You can clear them, which, as I showed you with that Irisat method, the irrigation one, they've clearly got rid of all the scripting part of it. There are some instructions for moving around and drawing and marking things. So you can put markup on a particular map. If I want to zoom in, very easy, just use the wheel on your mouse. You can get right down to this kind of level, okay, on that image. So you can move around very easily. And the great thing about it is that it's all done because it's Google. If I want to go to a particular place on Earth, that is so easy. I just go Richmond, say, and obviously there's a few of them. So we'll have Richmond, New South Wales, and just press Richmond, New South Wales. Why is that opening the catalogue? I said that, but I boasted how easy it is.
When it comes up, click on click on that.
That's the one. Here we go, and we're straight into it. Okay, and you can see that that's pretty much the image that we had from that previous the image that was from Nearmap that was in the lecture. So obviously, because it's the same place, so you can move around. Yeah, just give it a moment or two. Sometimes it is a bit slow if you do get impatient, but you can go anywhere in the world. So anything you're doing in terms of vegetation, you can do comparisons between two different places. It's very easy. You just dial them up. I've got other things in here on the left-hand side in this screen here. These are bits of script that I've written in the past. They're all mine. And over the time I've been using it, this is the teaching version. So I've got various tutorials that we go through. I've gone through writing script. Now, when you click on one of these, and I'll do the elevation for the moment, in comes the script. Now, you may be thinking, oh God, that looks terrible, but it's not actually that bad. It's asking for a data set from an image collection, a particular type. It's asking for the elevation map. It's extending the elevation over 150 pixels. It's giving it colors, and then it's displaying it on the screen. Centered on, and I bet you that's the Richmond thing. If we run it, let's run it. So what I'm saying is that once you've created some script on a particular application, you save it onto the computer, and it's there forevermore. And if I wanted to go somewhere else instead of using Richmond, because I'm pretty sure that's where it will run to, I can just change the map coordinates to some other area and it'll do the same thing in there. So I'll just run it. Now I can't see. Oh, okay. You can see that the layers are building here. Okay, there's only one layer building. This has got a false color map of the elevation of the Richmond area. And you can see that the way it's been set at 0 to 150, 0 to 150 feet. A lot of the Richmond area is actually at sea level. And you can see the high areas of the town. If I wanted to, I could put the satellite image, I can tone this down, sorry, and I can see, if I wanted to see where I am, I can just put the slider in to see what positions and where it corresponds to. And you can see that there are areas that will be below a certain level, the ones that are above a certain level. There's a slight problem dealing with Richmond in that we have very low land around the campus, and we have very high land around the mountains. So you can see that the mountains have whited out because it can't cope with the range, can't stretch the range of the palette across the whole thing. If I wanted to do that, I would change the variations in the elevation from a minimum to a maximum. I'd change them, but that gives, I could make this, if I change that maximum to 50, say, I would get everything below 50 feet, 50 meters, sorry. Okay, so I'll put that one in, I can run that again. And again, the beauty of this is that, so now you're getting much more detail in the blue areas. You can see how the blue areas, but we've got the scale now, shows you much more, it whites out at a much lower height around North Richmond. You've got much more detail of the contours of the river flats, and you've got these areas which are at higher elevation, and right at the top we'd have our campus, which is on the high point, which is obviously why they built it where they did. Anyway, that was just to show you that. We'll have a look at building this kind of map in a second, but that's what we do. We only save the script, and it calls up maps from collections, does operations on them, and then displays them on the screen. Yeah, it does put some context why it's so vulnerable. We'll see in a second that some parts of it are actually below sea level. Okay. We'll go through that. Let's get started, and I'm going to give you an exercise. Now, the easiest way to deal with these things is to copy and paste. Nobody, or very few people, write the script from scratch. You can find heaps of, there are communities of people publishing particular uses of Google Earth Engine all the time, and they will publish their script, and all you need to do is just apply it, copy it out, and paste it, because the beauty of it is it's just text. It's a whole load of lines of text you paste in, and you press run. It's as simple as that. And if you want to change where the area of the location, you just change the map center, and this number is the zoom It's a zoom of 13. The numbers go up to 20, and you just dial up a new area and see what it does to you. Does for an area of interest of yours. To find an area of interest is very easy. You just come out, and we can. Oh, this is going to do the whole thing for Australia, so I'm just going to stop. Yeah, I'll turn that off for a second. I'll turn that map off. But if you want to collect an area, you can go to an area, any area of interest, and you can find out what the coordinates of it are. It'll tell you its location. We'll do that in a sec. Okay, so any other questions? Any questions before we start? Let me go back to Richmond, New South Wales. Okay, and it's going into, I don't know what specific zoom it's zooming in at, but it is. Okay. Now, what I'm going to do, the first thing I would always recommend you do is put a geometry point onto the map. And that's what I was saying. You can do this with any point on the map, and it will give you its location. A marker just means that we can always go back to that marker whenever we want to. So you just click on that little sign, and I'm going to put it somewhere on the campus. Don't know where. Usually put it at the top of, well, it doesn't really matter. There's Hobartville. We'll put it somewhere on the campus. That'll do. Looks like it's on the, that's on the campus. Okay, now you can leave it. What's happened, as you see, is that when I clicked, it came in here as a point, and it's given it the title geometry. Now that's not always very useful, because you can end up with lots of places called geometry. So I call that campus. And you can see that the global coordinates of that are now marked here. So if I were interested in doing this anywhere else in the world, I would just put a map on it. It would give me the map marker, and then I can, the coordinates are known to me to umpteen decimal places. Oh, what's going on here? Okay, so we'll define the area of interest. Okay, so the next thing is that I want to have a look for I'm going to look at the elevation map. We're going to build pretty much this one I mentioned earlier, which is our elevation of our area. So what we shall do is type in, we need to pull up an image set. Okay, so if I want to know about particular image sets, I just go into the search engine, and I know that I can go for elevation, and it will come up with the various elevation surveys across the whole world that it's in the catalog. And the one that I want to use is STRM, but I want to use the Australian one, and I want to use, there we are, DEMS, which is the Smooth Digital Elevation Model for Australia. Now, there's two things you can do. You can either click on it, and it will give you all of the image about when it was collected, what bands of light were collected, and all of that and its use. And then I can press import. So I'm going to import that in. Now, when I import that in, that brings that in to above the line. You can see a line there. So when you're working later and it gets more involved, you can, instead of bringing the images in like this and loading them up at the beginning, you may just want to call them when you use them. So you can, if you have multiple image sets, you don't want to call the whole lot in at the beginning. That uses a more buffer size, so you can just call them when you need them. And you can see that those go in above the line. Now I'm going to rename that, and I'm going to call it SRTM, sorry. Smoothed SRTM. Okay. Add the image to the console and click run. So let's run. and there's nothing happens, of course, because we haven't got anything in here. But we can see, we should see, no task select. Oh, okay, because I haven't told it to do anything. So what I want to do is find out the information about that. So the instruction for doing that. Now, as I said, you can type everything in, but if you go to my notes and you just do, instead of typing everything, just copy, I go Control C and Control V. Okay, and I'm going to print. Now, print means give us all the information about SRTM. So I'll run that. Okay, there's not actually doing any task, but we've got the image. Now we've got all of the bands, all of the properties, all of the information is available to us. It's loaded it up into Google Earth Engine. So all of that information. Now, these are relatively simple. There's just one band here, which is the, that's how many pixels it contains. So you can see why the files are so big. That's just getting the elevation data. So it's basically a 2x2 grid with height data registered for it. But the bands can get very complicated with the multispectral cameras like Sentinel-1 or Sentinel-2. And here are all the properties. Okay, so you can get all of your information from there. Now, let's use this. And what we'll do is we'll do the most important one that you want is to see it. So I'm going to go to the next line, which is add a map layer. So I'm going to go Control C and paste that in. And now, so it will add a map layer called SRTM, and SRTM is this image. So as I say, the script is not hard to work out. So let's run that. Now, when you run it, you will see that a layer comes up, and as the image runs, it will disappear. So, and one thing you can do is turn the images. You don't want it running too many images at once, because that's what takes time. Each time it has to consult the internet to do it. And you can see, well, we can see one or two things. We've got, as I mentioned, let's turn the image down. There are certain areas which are appearing black. Now, what we've got this set to is that anything at sea level appears, sea level or below is black, and everything that's above sea level is white. So we've actually got areas around here which are below sea level. Okay, and that's what it's showing. Obviously, that's not great for information, so we need to adjust the visualization map because it's turning out completely flat. So let's get some feel for the information. Let's have a look what we've got for the whole of Australia, or for New South Wales. We'll run it. I'll turn the light down on it. Oh, sorry, I should turn it up. Oh, I've got it switched off, that's why. Okay, so that's absolutely what we're showing is everything at sea level or below. And then these little tiny dots are below sea level. And here we are in Richmond. Zoom in. Okay. All right, now let's try and adjust that. And so we're going to change it so that we're measuring heights or elevation between 0 and 300 meters. So that's what the next line does. I'll paste that in here. So we're adding another extraction saying, and we need to get rid of this one. We don't want it to do twice because that's actually printing. When it says add layer, map add layer, that means it's printing that actual layer. So we'll just get rid of that one. Actually, there's two ways of doing that. I'll show you another way. Okay, so this one will do between 0 and 300 meters, and it will try and take the range of pixels, which is 255 shades of gray, and scatter those between 0 and 300 meters. So we'll run that. Okay, and so everything in the region of Balcombe Hills and Castle Hill, that works beautifully for that. The problem is there's areas inside the Blue Mountains which are much higher than 300 meters, so that goes beyond the white limit. So black is sea level, white is set, so it's stretched 256 pixels between 0 meters and 300 meters, which is good. But everything above 300 meters, it doesn't measure. So if you were to want to do the mountains, you might change this to a maximum of, say, I don't know, 1100. And we'll start at 300. Start from our maximum. Do that again. Oh, didn't want to save it. Run it. And now you can see how the lowland is blanked out, but it's done pretty well at the mountains. So you do have, you have to remember, you've only got 255 shades of color or gray, shades of gray to play with. So you have to know something about what you're looking at to get the right ones in. This of course is absolutely useless for looking at Richmond itself. If you wanted to go into more detail about Richmond, like we did before, we'd start off at 0 and we'd go to, say, 60. And we'll run that. And go, there's the layers. And now we've got extreme detail around the river flats and our land. More detail, you see the pixelated image at the moment. So I've got to come back out again to get better resolution. Okay, so here we go. And we've got the channels across the river flats coming out, and the land that we have the campus on is here, this patch of area of high ground. Okay, so that's the very first thing. Now, as I said, there's two ways. When you're doing this, I'll put another layer in. Sorry, just well, if I don't want to run that map again, I can do what I did. It's just delete it. I can edit it. I can change these numbers. And one thing you might want to do is to switch between different types of maps. So if you go Control/ here, Control/, you can see that by doing that, you get double // on your map and it's turned green. Now that means that that is just text and it won't read it. So if I ran this now, it won't actually show an image. I can prove that to you like that. Okay, it's ignoring that. If I click on it and go Control/ again, it comes back. So you can put multiple different parameters in and just block them off from individual runs by Control/, which is really useful. The other thing is that using the double slashes, which you can write in, let's put a line in, and I put 2 // and I can say elevation map, print it, show elevation map. And that won't take part in that won't be read by the computer program because of the 2 double slashes in there. But it's really useful for when you've got long coding lines telling you what the individual bits of the code do. So you can give yourself notes by putting double slashes in, and it can even be done on real code just by going Control/ to switch them on and off. So that's really handy. Okay, well, now when we run this, I'll run it again. A couple of things about it. One is that the layer is coming up as layer 1. Well, maybe we'd like to give it a proper name. We want that name on the map to be actually a proper name. So I'm going to change that layer to Control+C, and I'll place it in. I'll copy over the top of this one. Okay, and I've given it a name. So it's got a minimum of 0. It's taken off the map that we've always been taking off. The curly brackets are around the heights. And then there's a comma and it says elevation above sea level semicolon or quotation marks. That means that when I run it, the layer will no longer be called layer 1, it will be called elevation above sea level. And you can see when you go to layers, I've now got one called elevation above sea level. I'd like it to be colored. Okay, so for that, you need to change the palette. And the instructions for doing that are in the line below in the tutorial sheet. You just copy them out. Now, this may show one thing you do have to be careful of. Control V. Yeah. Okay. When you copy and paste off a PDF and you copy it in, unbeknownst to you, it's got a carriage return. If it goes across multiple lines, it brings in a carriage return with it. If I run this, I'll get an error. Even though the code is correct, it's saying, go to this map. Here's the palette. Sorry, here's the elevation. Here's the palette. We put it into red, blue, or green, red, blue, and yellow, and call it elevation above sea level. That semicolon is the carriage return in Google Earth Engine. However, it's going to give me an error because there's a carriage return here, which I can't see. Oh, well, I've confidently boasted it would make an error, but it hasn't. You do have to be careful. I think much safer, as I've found in the past, it's working actually. I don't know why the carriage return's not there. Do that, okay? Just so that it makes more sense to you. And also, yeah, sometimes you will get errors come up. You will get errors come up. Obviously, it was reading across that line, but a carriage return comes in sometimes when you copy and paste text in, but that one's working fine. Okay, and as I said, that now makes the areas is particularly good for the areas around Balkan Hills and to the coast. It's no good for the high end is red. So blue is the low end, yellow, red. It's colored, and you can change these colors to anything you like. I can put green in here if I wanted and run it. And the beauty of it is you just have to edit the text, change it to what you want. Okay, now for better visualization of for slopes, okay, there's other maps which are they're calculated from this SRTM data, and one of them is hill shading. Okay, so I'm going to add this line in the next one, and I'm going to bring that in, and the next line on the instructions brings in, and what this is saying is bring in the hill shading based on SRTM, and they have an algorithm for doing that, and it's going to go for, oh, that's not particularly high, minimum 155 to 255. Don't know why I've got those in there. Okay, we'll just see what it gives, and we're going to show it. What's the hill shading look like? What I will do is I'm going to turn off the previous one, which, as I said, is useful. So go to that one and go forward. Okay, so it turns it into text. I'm not interested in doing that. I'll just look at the hill shading and run. And so you can see what it's doing is it's giving a false shade. It's imagining that the sun is coming from the left over this terrain, and it's generating an image which is based on, yeah, seeing that image from the side, like it's giving a false dawn, if you like. It's like imagining raking light going across the surface of the elevation. So if I turn that button back on again, just go Control// again and run it. And I run the two together. We're not going to see the effect of that until, as you can see, it's a bit slower. Here's the second map coming in. And what I want to do is kind of blend those two maps. So I just change the opacity on the hillside one, because that's the top one. And you can get the effect of one superimposed on the other. You can get quite a detailed map of the elevation. There is another way of doing this, working a similar way. This one's called slope. It works out slopes of land based on calculations that it does inside the computer, just like the other one. I'll turn this one off. So I'll make that into Control/, turn that into text. I've got that one and that one. I'll run them both. And I hope you can see that, as I say, the beauty of this is that everything is working off a computer it's not working on your computer. It's able to do this by connecting to Google Earth. Sometimes, of course, that does mean it's a little bit slow, but I've not really found a problem. I don't no idea what size computers that they've got, but this is showing contour maps now, showing on the basis of contours. So higher areas of height plus the various contours of the steep ravines that we've got through the Blue Mountains, the various patterns inside the hills area. And here we are in a relatively flat area. And again, we can change that. That's the slope line here. I can change the thing to 300. I could do it more detailed on here if I change this to 50. Run it again. Green run again. Run. And now I better zoom in on this. It's going to put the second layer on top. Contours are going to go in. And of course, there's not much contour information from somewhere that's so flat, but still do it. I'll make this less opaque. And then I'll zoom in on it. So here we are on the campus. And so this gives us the contour information superimposed on, and you can see that every time you zoom or move, it recalculates the map, and that can be a bit slow. So there we've got the contour information coming up on the image. So we've got individual high points around the campus. Okay. So that gives us a basic map. And now I'm going to ask, now we're going to do one other thing. Turn that off. We're going to start asking questions of the map. So I want to go Control V. Oh, not Control V. It should be Control /. Sorry. I'll turn that into text. I'm going to add a variable. I'm going to say, oh, by the way, if you want to, you're finding it hard because it's more, it's quite dense, you can leave blank lines, and that doesn't matter. So now I'm going to create a variable, okay, called, taken from the STRM, that's our elevation map, of greater than 200. And we're going to add a layer saying, show me everything above 200 meters. So I'm going to print the map. I've changed that back to 300, 150, no, 300. It's going to spread the red, green, yellow across the 300 meters, and then just show me every area on the map which is above 200 meters. So if you were okay, so that's everything. Oh, it's got the wrong way around. White is coming up as greater than 200 meters, everything above. Okay, so let me just bring that one down so I can see. Okay, so this is where 200 meters starts. Everything on the map above 200 meters is appearing white. Everything below is appearing black, and it's still showing us the elevation above sea level map from before. Now, what's the use of that? Well, if I want to work out flood risk, one thing I can do is change that number to 200. Instead of 200, let's make it 50. 40. What's the effect of a 40-meter flood on our area? So let's go to 40. And we'll change that to 40. That's just the text, so it's not essential, but okay, we'll run that. And we can now see all of the areas. Is that doing that right? Greater than 40? Yeah, it's good. Bring that down. So if we had a 40-meter flood, that's the area would be taken out when Richmond would completely go underwater. But even more realistically, a 20-meter flood, which is what we had so recently, we changed that to 20. Run that. You can see the islands. A 20-meter flood will leave our campus. That's pretty much the only island in the Hawkesbury. By taking those layers and turning down their opacity a bit, okay, we can see the areas of Richmond which would survive a 20-meter flood. And obviously we can change that number, but we're getting to realistic numbers of what happened recently. So let's make it a 10. Let's see what a 10-meter flood does. And this is quite common around our area, of course. So I'll run that. Again, we'll turn it down. Okay, and that's typical of Rickaby's Creek and South Creek entry, and there's the railway comes through here. Okay, so from Mulgrave, the railway goes to Windsor across here, so that's flooded. There's Rickaby's Creek flooded. This shows you exactly what happens every time we get a 10-meter flood. Okay, so that's one. So there's a computation. We just say add a map layer of the height of everything above 10 meters. Open brackets mean everything. And again, you don't really need to know. Once you've got a line that does that there in one program, you can always copy it out, try it, and nothing is going to break if you get it wrong. And you just then alter the text to what you wanted to do. You just fiddle with the text as needed. How are we doing for time? Okay, 32. Okay, let's add, do another computation for the slope, on which we get a third parameter, which gives us, it gives us the slopes. We'll just add that one, do that one quickly. And I'll add that in. I'll turn this one off. Oh God, I've done that again. There we go. And I'll turn this one back on, which is just put, I accidentally turned it off. And this will give us slope, and it will give us a maximum minimum slope level. So let's just see what it does. So here's our terrain. Still measuring between 0 and 300. And here's our slopes. So this is actually showing where's the steepest slopes in an area. Okay, so it's showing you on a scale of 0 to 60 degrees. This is the slope that we get. I'll just bring that slope level down. Oops. Yeah, you have to play this a bit carefully. I'll actually might turn that one off. The elevation map. You can see areas where the slope is highest, the steepest parts of your terrain. Okay. Now, one thing that we will want to do is we will want to define areas that of interest within a map. Okay, so you want to define a particular area, and to do that, you use what's called a spatial reducer. That's a geometry, and these are the tools that you use for creating them, which will define an area of interest within a bigger, broader picture. So let's do that. So I'm going to turn off all of these. Oh, I'll turn off that one. I think that's the only one that's still open. Control/. Yep. I'm leaving them because I can always turn them back on. I don't want to have to always type them out. And that's a handy thing to do, is to just, if you've got something for the future, just turn it off in here. Turning off the calculation code as well, because that too can take up time. And I've just got the one map layer that I've got in here, and then we can work off that. So let's do this. Okay, and I'm going to take in that piece of code that's in the thing. Oh, I've got some messages. Sorry, I haven't been through all the messages. Oh, Meg, yeah, let me just answer a couple of the questions that have come up. The images are as recent as yesterday. If they had a satellite came over and collected a particular image yesterday. One of the things I do want, one of the things we'll do, it's not limited to FUDs, no. The Google Earth images, no, they're Google Earth Engine. They are the satellite images collected by all of the space agencies, kept in a database. And as I said, obviously, when you're looking at elevation data, like I'm doing here, that doesn't need to be updated that often. Okay, so there's been one mission to do that. But for the vegetation data, they are constantly going round and round the Earth, okay, and collecting the data. So it is up to date for whenever the last image of wherever you're interested was taken. And you can set the dates to search through the catalog. And one of the things that this tutorial does is take you through a search of how to do the search through the catalog, pick up a particular image, and then check, does it have cloud on it? And so maybe you say, okay, I'm interested in a particular time period, but I want to make sure I've got no cloud in it. So it can search through a group of data to get the cloudless images in there. So, yep, not images of flood, they're up to date and they're constantly being updated. It does depend on the satellite area, you're correct, image. Okay. And yeah, so you find the satellite image, you just search for a date. At the moment, see, what we would do is we would look for, if we wanted to look at the dates, the vegetation index for this, I might go to something like Sentinel-2. Okay, Sentinel-2 is the multispectral image at level 2A. Okay, if I get the information on that, this is constantly being collected. This is the European Space Agency information, and it picks up things like aerosols, and if it's looking for pollution in aerosols, so smog, it picks up for blue, it picks up green, red, it goes near infrared, sorry, the red edge, there's two different ones at 20-meter resolution like that. There's the near infrared, and there's a fourth one. I don't know what that one's for, but then it picks up water vapor, which helps with cloud. And then there's the shortwave infrared. So there are 12 different bands of oh no, there's more. No, 12 bands of information. Oh, I haven't even used some of these. Okay, the optical thickness, I think these are calculated fields, but there are 12 bands. Labeled as bands, okay, and these are calculated images based on those bands. Okay, so those are the kinds of things you can get, and this is the what it will look like. So pretty cool, and that will be up to date depending on the dates you search for. It'll collect that data for change it from complete black and white to colored like yours is now. You just name it a colored. Zach, I'll show you in a sec. So it's from this instruction. You say, this is, because we're dealing with height, okay? Palette, green, yellow, red. There are different ways of doing it too. You can actually name, the colors. You'll see, but this is the simple. And if I wanted to, I could change it to whatever. I wonder if it does pink. I've never even tried it. I'm not sure if it does constructed colors. Yeah, it's just pink. Okay, so it pretty much has all of the colors, even if they're not standard colors like pink, probably just purple. I might change the green to purple. Oops. Yeah, okay. So now I've got purple, pink, and red. Anything you want. These are false colors, of course. And the purpose of false colors is to choose them so that they draw out the information that you want it to show. Okay, now did I put that data in? No, I'll just do this one. So now I'm going to turn that one off. And that should do nothing now. Yeah, good. Okay. In the beginning, we put a point on using that point and said that's the campus. If I wanted to get information about a region, then I can use these polygon tools, and there are a few of them. I can draw a shape, I can draw a regular square, so I can define an area using that. So I'll do that. Take a polygon. It's going to give me a new layer. This is tricky because you have to remember when you click on one of these tools, you do have to go to new layer. Otherwise, it will change your original one, which was your point called campus. And I've been caught out so many times with it. So here's our new geometry. Okay, let's put it in here, called it geometry, and it's going to define something. So I'll go around. Oh. Ugh. Draw a shape. Why is it not working? Let's zoom in. There's my geometry. I might be doing a new one. Oh God, I can't get the damn thing to draw. New layer. Oh, I've got draw. Oh, here we go. That's exactly what I wanted to do. So I've done it off the line drawing, and I can come back. So let's say I've just cordoned off an area of the campus. Okay, so now my area is joined up. Okay, so I can now define what I want for that. I'm going to actually delete that one because I've got rather a lot of them. Yeah, and I'm going to get rid of that one because I didn't define it very well. And I'm going to do it off a square because it's just easier. Okay, so I'll draw a square over this area as my geometry. And then I'm going to add in the text that's below the spatial reducer. Now I'm doing all of this off elevation data, but that's just so it's because it's simple to deal with because I'm doing it with one layer to begin with. And so I'm going to add a map layer, which is going to go from 0 to 1,000 now. So it's going to do the whole of Blue Mountains. It's called DEM. It's going to add a map layer called geometry, okay, which is going to be the reducer on the scale thing. And then it's going to print up here. It's going to tell me what the average elevation of my area that I have defined is. So let's run it. Oh, geometry is not defined. So there's what happens when you get an error. It's very good with spotting errors and telling you what they are. I haven't got anything in here called geometry. No. What is that thing called? Oh, it's called campus. So I've done exactly what I warned you about. I didn't put it in as a new layer. So I'm going to redefine that campus as call it geometry. I've lost my marker in doing that. run it now. See, the error's disappeared now. And now if I look up the properties of this, it will tell me the average elevation of that area that I've defined is 20 meters above sea level. If I move it, and one of the nice things is you can just shift these things. So I can redraw my map. And I'll move it over to the Blue Mountains and run it again. Same thing, it's just changed its position. So if I'm looking at areas, okay, it will recalculate that and tell me my elevation is now 307. The average elevation in that area is 307 meters. So you can just define your areas using these geometries. The tricky part is remembering to make sure, like I got caught out, that you have to have whatever you're searching for here, saying geometry is geometry, that name, add map layer called geometry, that has to match whatever you've called it here. So if I called that mountain, for instance, now it won't run. It'll give me an error. Oh, why is it working? I have no idea. I've got mountain, geometry collection. Got a variable. It seems to have, oh yeah, it's called it. It's updated it. Okay, that's neat. That didn't used to do that. It's actually, yeah. This one's actually working by managing it. So I think I would like to call that geometry. Now it will fail. So it actually updated. It didn't used to do that. So something, yeah, geometry is not defined. So you have to define it as mountain because that's what we've called it. And you do have to, those kind of things are irritating when they happen, but they're all your fault. And this, remember, yes, somebody's just mentioned, I think it might be Zach, it has to be lower. This thing is case sensitive. So one of the things, look, if you look at, say, when you're typing in reduce region, one of the things of computer code is that the capital letters don't necessarily appear at the beginning of the word. You have to get them in the right place, otherwise it will fail. So a lot of the things that come up is when you're debugging what you've done, because you've just spelt it wrong. You've done something silly and you've typed it out like you would do in normal language, and it's not normal language. Okay, now we're getting close to the end of the time for today. But what I want you to do is just quickly, I'm going to bring in this stuff over here, which is the exercises that we've been going through. And what I'd like you to do is try it out. Okay, I've got some thing in here. This is on variable bands. This one's from the Copernicus system, so they all come in as different bands. This is Sentinel-2, and here's what I mean. This is the address of a particular image. Okay, and that is, I know, is the 6th. It's the 16th of June, 2020. Okay. That's what that part is, the date, but goodness knows what all that lot is, all of that. So they've got huge, each time that satellite goes around the Earth, it takes multiple images. So this address returns to a specific image by date, time, path. Okay, now this one is chosen deliberately because it doesn't have any clouds on it. It's the first one I could find that had no cloud. So there we go with that. Follow that through and you'll find out the multispectral imaging bands. If you stand back, if you zoom out, you can see that the image, even that, what you can do is search for an image that covers a particular area, which is one thing that this thing does. You can see that that particular image took an image of a whole chunk of New South Wales. And just as a word of warning, when you're choosing a place, choosing, say, a dot, like our campus marker, it could be right on the corner of an image. And so when you try to look for information above the campus, north of the campus, you may find it's not on that particular image because that particular image didn't have it in. The next one round may have taken a slightly different image, but that's the area that was covered by the single shot that the thing took. This is red, green, blue, band 4, 3, 2, and it shows you setting the colors between of red, being blue between 0 and 3000. You can change them. You can change the colors. This is called, we call this one tree color. This is a vegetation index. This one is what we call the NDVI, or in this one's not NDVI, but it's definitely a vegetation index. Oh yeah, so this one is using infrared, red, and green. Okay, it's taken out the blue out of the color, which is why the rivers are appearing so black. But it's taking near infrared. Remember, the near infrared absorbance was important for vegetation. So by bringing in near infrared, red and green, you've now got an image which highlights the areas of highest absorbance. So you can see differences between bushland, kind of this, there's to say grey red color, and highly irrigated regions such as that. And you'll be able to see that on the map. Then there's different indices. Now what you do, as I say, is in the instructions, is that you can play with these numbers. You can use different bands, and there are a whole load of indices that are used. Natural color, that's red, green, blue, is that. There's the false color infrared, that's the one I've just shown you. There's things that emphasize urban, built up urban areas. If you use bands 12, 11, and 4. Agriculture uses 11. I can't remember what band 11 is, but 8 is far infrared and blue. Land and water, obviously that's that one. So there are different indices. Just try these out, okay? And then this one is on cloud. Yeah, it tells you about how you filter them to get the cloudless image. So this is about cloud coverage, getting rid of the clouds coverage in it. And if you do that and have a go at it, you can get on to what's called the normalized difference vegetational index. This is one way of doing it. It works off the bands 8, 4, and 2 of the spectrum, and it produces a gray color image, which is very high, and you can change the color. You can change the color to brown, yellow, red, or whatever colors you want to, and it will show high areas of the vegetation index. Tells you the areas which are growing, actively growing most strongly in your area. And of course, if you measure it over time, you can do a comparison or plot a graph to show how the vegetation areas fluctuates depending on rainfall. You can correlate that with rainfall and stuff. I think we're on campus, yes, for next week, Abida. Aren't we? I think, Ricky?
We are in the computer labs.
Okay,
so.
Cool. Are there any questions any of you guys have got to ask before we finish today? Don't be afraid. Anything you want to know, I would like you to try it out. So first thing you've got to do is register. That usually comes through pretty quickly. The message about registration goes to whatever email address you put in. And I'm saying I highly recommend using a Gmail account for it, because everything is Google then. So it'll go to your Google account, register. Then when you sign into Google, it recognizes where you are and you can go straight in. You don't even need to put the signature in. So that's really easy. And try these things out. Just follow that tutorial down, and we can then be on the right page, and you'll be at the right level to do these exercises that we'd like you to try out. Okay. Right. Well, Ricky, if that's everything for today, if that's okay, I think we'll finish off there. Do you, Rick?
Yeah, thanks. Look, it's really powerful stuff here. So, but the main thing is, it's going to be, you've got next week, but also in between, just play around with these, even if you just do the basic elevation, playing with script and that sort of thing, just to know what you're doing, be able to move up, change the colors or change the, those sort of things are really important just to get started with that.
Yeah.
And then you can build on it. You can always
and don't worry about, I mean, one thing I didn't actually say is that, you just save your files afterwards. You can save your script. You can't damage anything by making a mistake, because you're just calling stuff off the thing. So don't be afraid to try things out. And if you really want to, just Google.
Yeah. I just Googled some, and it came in.
Yeah.
I went for something a bit more complicated, and then it worked, and then one little bit didn't work, and it popped up where the error was.
Yeah,
and
exactly.
So next week we can, if you saved it, we can try and work out where the error. It was clearly finding a wrong part of a database, and so they're the kind of things that
I'll cut this. I'll crop this out, and that's the thing you can do. There is a whole community of people trying different things out with it. Some really serious applications for it. You can just grab the data, and all you need to do, like with that thing that Ricky's put up, just copy it out and paste it into the command line. Now, some of the things you will have to watch when you do that, I'll just do it now, is that, where the heck is it? Here we go. If I go, I'll reset. So just clear the script. So that's how you reset. If you want to save, you just press the save button. This is the stuff that Ricky put up, and we'll run that.
That one worked actually, but it takes a little while because it does.
Yeah, it's got 2 layers of maps.
It does more than the. Oh, there you go. You've got a faster computer than me, so.
This shows the fires when they were happening, isn't it?
Yeah. So no, this is a really interesting one. It actually takes into account temperature data and fires at the time, and then actually predicts a fire risk, and that's the region that was defined. So you can do that, and that was I googled that, and
excellent.
So they're the kind of things, but I'll Google another one around.
That's really nice. That's really nice. Very nice. You can see how it's following terrain around here too. That's off the MODIS. And MODIS is the temperature satellite. It creates localized temperature differences.
So what it's done is actually take several sets of databases there, and almost do a prediction based on temperature and active fires, like as in over a period of time. You can see that from first to the 31st of the 12th, 20.
Yeah. So what it's doing is it's taking a set of data in between this date, these dates. Okay. And then it's looking at those images and say, do any of these maps have anomalous temperature changes from the previous map? So is this one, if it's got a little area that's jumping, well, where is that? And then it's calculating the average temperatures. Yeah, it's cool. That's actually a very efficient way of doing it. I've got another one there, which is slightly less efficient. But yeah, and then guys, all you need to do is press save, and you give it a name, save as, and you just put your title in. So we call that one Ricky's
ripped off Google bushfire. Yeah. So I'm just going to quickly jump in here. I know it's 2 minutes. These are the kind of things that, and we'll talk a bit more about the ecological modelling, which we'll do the week after. So other stuff will go on. But just quickly in terms of the assessment, which will be released here, what we wanted you to do is actually do a video almost like this, but just for 3 minutes, just to kind of demonstrate what you've done, and actually understanding that you can in your video you can say that, look, I've taken this database to actually do a test a question or doing that sort of thing. It just has to be very simple, but we just want you to kind of show some understanding here about the skills that you developed here, and actually what what it potentially means.
Yeah.
And we will talk more specifically, and there'll be more on views about that. But this is what this is all we want you to do to actually demonstrate these skills through what we call a 3-minute thesis. So it really is there just for 3 minutes just to demonstrate your skills here, and you can do that like this over Zoom and record it. And but like I said, there'll be a lot more detail, and we'll talk more about it. And you'll have an opportunity to use this or the week 4 ecological modelling stuff to actually just demonstrate in one of those presentations. So yeah, look, it's there are lots of resources out there. Go find them, play with them.
Yeah.
The most important thing there is that, you don't have to write your own script. There's lots there. But what we want you to demonstrate is that you understand what the script means and why, where it's come from. So
exactly,
it is 11. So I understand you guys probably have something else on and that sort of thing. So
okay.
Anything else do you want to wrap up, Richard?
Yeah, no, that's absolutely fine. That's great. Yeah, just go for it, guys. There's heaps of questions you can ask of this once you start thinking about them. Yeah. Okay.
Cool. Thanks, everybody. Richard, can you hang on just for a minute?
Yeah, sure.
Thanks, everybody.
I'll just stop sharing my screen.
And I'll stop recording.